Have you ever stopped to think if there's a fundamental pixel size to our universe? I mean, a point where you just can't zoom in any further. Well, let's really get into this question because the answer, oh, it turns out to be one of the most mind bending ideas in all of physics. It really seems like such a simple question, right? If we just keep building better and better technology, can we keep magnifying reality, just peeling back one layer after another forever and ever? Or does nature itself at some point just put up a big stop sign? For hundreds of years, the answer has been a clear, yup, we can keep going. I mean, think about it. First, we got microscopes and saw tiny cells. Then, electron microscopes showed us individual atoms. Then, we built particle accelerators to crack open protons. With every new tool, we've found a whole new, smaller world hiding inside. Okay, but to understand where this incredible journey might actually end, we need to talk about the basic physics of how we see anything at all. There is a fundamental rule book, and we have to play by its rules.
And the master rule, the one rule to rule them all, is wavelength. See, everything we use to look at stuff, whether it's light or electrons or whatever, it all behaves like a wave. And to actually see an object, the wavelength of your probe has to be smaller than the object you're trying to see, period.
And this is just the perfect way to picture it. Imagine a ship out on the ocean. If these huge, long wavelength waves roll by, the ship just kind of bobs up and down. The waves barely even know it's there. But if you have small, choppy, short wavelength waves, they smack into the hull and scatter all over the place, revealing its shape. Those short waves can see the ship.
So this sets up a crucial chain of logic. To see a really small object, you need a probe with a really short wavelength. Makes sense. But here's the kicker from quantum mechanics. A shorter wavelength always means higher energy. You can't have one without the other. They are locked together.
And all of that gets boiled down into this beautiful little formula, our master equation for this whole explainer. It's basically a seesaw. The energy you need, E, goes up as the size you want to see, delta X, goes down. You want to see something 1,000 times smaller? You need 1,000 times more energy. It's that simple and that powerful. So you might be wondering, okay, that's the theory, but has this strategy actually worked? Oh yeah, it has worked spectacularly. Let's head into the subatomic world. Just look at the leap in energy here. To resolve an atom, you need about 150 electron volts. You could practically get that with a battery. But to see inside a proton, which is 100,000 times smaller, now you're talking over 1 billion electron volts. You're going to need a huge particle accelerator for that. The energy just skyrockets. And boy, did it pay off. Back in the late 60s, scientists at Stanford blasted protons with electrons at 20 giga-electron volts. And what they saw was amazing. The electrons were bouncing off these tiny, hard little nuggets inside. They had found quarks. This was proof positive that our master equation was the key. And that brings us to today, and our undisputed champion of microscopes, the Large Hadron Collider. This monster smashes particles together with a staggering 14 trillion electron volts of energy. That's almost 1,000 times more powerful than the experiment that discovered quarks. So you see the trend, right? This begs the obvious question. Is the only thing stopping us just our ability to build bigger machines? If we could build an accelerator the size of the solar system, could we just keep zooming in forever? And the answer, incredibly, is no. A hard no. Because you get to a certain point where the very strategy you're using, the very rule book we've been following, it turns against you. Nature itself throws up a roadblock. The limit isn't our budget or our engineering skill. The limit is gravity. So here's the twist. Einstein taught us that energy is mass, and that mass and energy both warp spacetime. So when you try to see something ridiculously small, you have to use our master equation. You have to pack a ridiculous amount of energy into a tiny, tiny space. And if you pack too much energy into one spot, well, that spot collapses under its own gravity and you create a black hole. And there's a name for this point of no return, the Schwarzschild radius. Think of it like this. For any amount of energy, there's a critical size, a tiny little bubble. If you manage to squeeze all that energy inside that bubble, gravity takes over and it's game over. It collapses, creating an event horizon, a one-way door from which nothing, especially not the information you were looking for, can ever escape.
And this leads us to an absolutely stunning conclusion. If the very act of looking too closely can create a black hole that hides what you're looking at, then there must be a smallest possible length, an absolute floor to reality. Let's figure out what it is.
So the whole game breaks down at this one crucial moment. It happens when the region you're trying to see gets so small that the energy you need to see it is exactly the amount of energy needed to turn that region into a black hole of the very same size. Your probe creates an event horizon that's as big as the thing you were trying to measure. The experiment literally swallows itself. And when you run the numbers, when you set the probe size equal to its own Schwarzschild radius and solve for the length, you get this: 1.6 times 10 to the minus 35 meters. This is the Planck length. It's not a technological barrier we might overcome one day. It seems to be a hard limit written into the fabric of the cosmos itself. And trying to visualize this number is, well, it's basically impossible. This chart doesn't even come close to doing it justice. Here's an analogy. If you were to scale up a single proton to be the size of our entire observable universe, the Planck length would be about the height of a tree. It is incomprehensibly, fundamentally small. So what does this all mean? If distance itself just stops making sense at this tiny scale, what is reality actually made of at its deepest level? Well, this is the absolute frontier of physics. This is where theories of quantum gravity come in. On one hand, you have ideas like string theory, which says that deep down, everything is made of tiny, vibrating strings that have a minimum size. On the other hand, you have loop quantum gravity, which suggests that space-time itself isn't smooth and continuous, but is pixelated, made of tiny, indivisible chunks. In both cases, the smooth reality we're used to is just an illusion. And that leaves us with this final, truly mind-bending thought from physicist Nima Arkani Hamed. He points out that whenever we've hit a limit in physics where something just can't be measured, even in principle, that something turned out to be just an approximation of a deeper reality. And this time, the thing we can't measure is distance itself, which might mean that our entire concept of space and time is just an emergent property, an illusion, hiding a reality that's far, far stranger than we can possibly imagine.